Hello, and welcome to Dragon Mathematics, where I am Dragon, and these are the mathematics. Today we're talking about the dreaded or perhaps beloved, depending on who you talk to, trig identities. We briefly spoke about this. It's called the Pythagorean Identities. The first one being that sin² of x plus cos² of x equals 1. Probably the most commonly used trig identity ever. Very useful in a lot of situations. You may be in a different class in a different semester and you'll have a 1, but you'll break it into this, right? Or you'll come to a conclusion. You'll come to the end of your problem that has like something plus sin x plus sin² x plus cos²x, and the problem would make a whole lot more sense if you just had an integer value over here, or a 1, or if this was 2, right? You'll eventually just say you'll be doing this all day. This is 1. You'll over and over and over. It's the most common trig identity, I would say, that is used in math, physics, geometry, engineering, all the things. So as I said, this 2 here is going to say, okay, I have 2 times sin² of x plus cos² of x, which means you may also end up with this in a problem, plus remember something, all right? You'll end up with this in a problem, and then you can just quickly in your head, you'll be like, okay, I can get rid of both of these and just call it 2, because when I am adding, if you just pretend this isn't here, and you're adding those 2 sin² plus 2 cos² is equal to 2 times the quantity sin² plus cos² of your variable, that's x currently, and this is 1, so that would be equal to 2. Another one of the Pythagorean identities is that tangent² plus 1 gives you secant². Less intuitive to just see and use like that. I will say that this one right here came to me much more quickly, and I was using it all the time. Whereas this identity, it was like, I would sit there at a problem and I would only have this, and I would be like, why? What am I supposed to do with this? But if I had done this, then I would have had an easier time with said problem. And so also keep in mind that secant² of x is the same as 1 over cosine² of x. So the idea of these identities is that you are going to have these true things like this. The fact that this is true, you're going to have these different representations of the same quantity or same value appear in your work. Like I said, whether it just be for math for the sake of it, or out there in applications in engineering, physics, whatever. And you may come to a conclusion that has this value in it, but your problem would actually be solved if you happen to have something in the form of secant. I'm being very general right now, but that's pretty much how it works. That's the point of using the identities is, this is technically an identity as well. This is just, I guess, labeled as reciprocal identities or basic identities, right? I sort of say that secant is defined as 1 over cosine of x, but that's not necessarily true. Secant is defined as the secant of x, that function. It just happens to be that if you take the reciprocal of secant, you'll get cosine, and if you take the reciprocal of cosine, you get secant. So this is also an identity, one of the basic trig identities. Just know that 1 plus tangent² of x is equal to secant² of x. So if you see secant², you also have a tangent² plus 1. And if you have tangent² somewhere, well then, also the correlate, you have to remember the correlate. Correlate almost just means an identity that comes from an identity, right? So the correlate says, well, if you do a little bit of algebra and you subtract subtract 1 from both sides, then you'll have this, right? And so this is, oops, what did I do? Minus 1. So it is true that tangent² of x plus 1 is equal to secant² of x, and that tangent squared of x is equal to secant squared of x minus 1, and they're both true for the same reason, so these are technically the same identity. It's just that you do a slight manipulation algebraically. So again, correlate just means if A plus B equals C, then A is also equal to C minus B. If A over B equals C, well, a correlate of that is, well, it's also true that A is equal to BC, right? Because then you multiply B by both sides. So another one of the Pythagorean identities is cotangent squared plus 1 equals cosecant squared. And I think I'll probably prove these to you because they will all bring you back to this one, the most basic Pythagorean identity. They're all these tangent squared of x and this cotangent squared of x are basically just correlates of sine squared of x plus cosine squared of x equals 1. So I can show that by saying, okay, look, I'll divide both sides by cosecant squared of x, which leaves us with cotangent squared of x over, or here, I'll write out all the steps, right? And then if you have a fraction like this, where the addition is happening on the top in the numerator, then you can split it. You can't do that if it's in the denominator, but you can do it if it's in the numerator. So I'll say 2 squared of x, cotangent squared of x over cosecant squared of x plus 1 over cosecant squared of x equals 1. Okay. And this is a little weird and possibly messy feeling, but hear me out. So cotangent is the same as, and you have to go to the original identities. So the identity of cotangent, the identity of tangent, right? Cotangent being 1 over tangent, tangent being sine over cosine. So cotangent is cosine over sine, so I'm writing that. Cosine squared of x over, all right, I'm going to write this here. Cosine squared of x over sine squared of x, okay, over cosecant is 1 over sine, so I'm going to write it. Remember, this is a crazy mess that I'm making, but it's just to show why we should accept these identities as true. 1 over, sorry, I'm not going to do 1 over. Here I have 1 over cosecant squared of x. That is the same as sine squared of x. We know that to be true, equals 1. And then remember that if you have top divided by bottom, and they're both fractions, that's the same as the thing on the top times the thing on the bottom flipped, right? And I see here that something being divided by sine squared is being multiplied by something with sine squared in the top, so we just cancel those. So that's cosine squared of x. I don't have to put it over 1, I'll just leave it. Plus sine squared of x equals 1. So there, that's the original identity I was speaking of. And that seems like a lot of flipping around and assuming and just thinking, what is the identity? I'm just going to plug it in and start going. But it seems like a lot at first, but it's actually simpler than you think. Again, once you do it a few times in practice and you start seeing these pop up, you realize there's only so many, like I said in a previous video, there's only so many trig functions, right? Like this function tangent here is just a combo of these two right here, right? It takes sine and puts it over cosine. So it's like, it's not a third function. It's easy. It's just these two functions, one put on top of the other. And then, right, same goes for all these. Cosecant, oh, I have 6 whole trig functions to work with. No, not really. You just have the reciprocal of sine and the reciprocal of cosine. So you're just flipping fractions, reciprocals, plugging in. I would say a golden rule for doing problems in a trig class that require you to show an identity or use trig identities to solve a problem is if I see anything like this, right? If I see any of those, I'm trying to get them into sines and cosines. Now, don't hold me to that. That's not the only thing that you're going to experience, but in general, though. Remember that sign being odd, if you have a negative argument, then that's the same as the negative of the sine function itself on the positive version of that argument. Cosine being even just says that it doesn't change. It doesn't care, right? And then tangent is the same rule as sine, because this should be intuitive. Tangent is also odd and has the same rule as sine, because if you broke this down, you would do sine of negative argument over cosine of negative argument, which is the negative of the sine of regular x here, over cosine is even, so it doesn't care. And then look, you acquired this minus sign. So that equals negative tangent x. Just a quick way to show that. So sine is odd, cosine is even. Tangent is sine over cosine, and an odd over an even function is going to give you an odd function. Okay. So far everything we have is that these are all the identities we have. That tangent equals sine over cosine, secant equals 1 over cosine, cosecant equals 1 over sine, cotangent is the reciprocal of tangent, I'm not going to write it. That sine squared plus cosine squared is 1. Tangent squared plus 1 is secant squared, which is technically a correlate of that, I proved. As well as cotangent squared plus 1 equals cosecant squared. You can start to see a pattern too, right? Tangent squared plus 1 is equal to 1 over cosine squared, and cotangent squared of x plus 1 is equal to 1 over sine squared, right? I remember, like, when I first started learning, I considered these so different from, I was like, 2 things to remember. It's really not, right? It's like, if you show me this top one, maybe I don't automatically think this in my head, but if you tell me the second one here, I'm like, well, yeah, I can see how that's going to work out if I, again, expand all these into the sines and cosines that are relevant. And sine is odd, cosine is even, tangent is odd again. So that's what we have so far. These are all our identities. All right, next, if you're bored so far, now's your moment, okay? So we have the sum of angles and the difference of angles. Right. So, say you have this. You have sine of some variable, let's call it capital A. You have sine of A plus B, right? For whatever reason, these are incompatible. So the reason that this will come in handy in the future is you're probably wondering, well, if A is 4 and B is 3, why wouldn't I just add them up to 7? Or if A is pi over 2 and B is pi over 6, why wouldn't I just find a common denominator and then add them together? Well, what if A is, 3x and B is 7y, right? You're not going to be able to add those together. Or, another circumstance may even be if you had sine of some simple thing, well, there may be an occasion where you want to split it into sine of 4 plus 3 for some reason. When you go through and start solving problems that relate to physical systems, that relate to computer circuit boards, that relate to charges and currents and electricity and objects moving at certain angles with respect to one another, sine of A times cosine of B plus cosine of that A angle times sine of the B angle. Okay? This is your first one. Okay? This can also be proved. All of these can be proved. I have to determine which ones I'm going to prove because we only have a certain amount of time in our life. So there's a difference between the angles. Right, so you want sine of the difference between the angles. Well then, and you'll be able to remember these as you practice with them, and they will pop out of your head, like I said, when the time comes and you're solving a problem or you're on an exam. But at first it's going to seem like a lot of writing things being multiplied together, etc. But there is sort of a pattern that I'll go over once they're all written down. So when there's a difference, it's sine of A times cosine of B minus cosine of A sine of B. All right, and then the next is if you want to do the same thing, but you happen to have a cosine. So the cosine of two angles being added is cosine of A cosine of B minus sine of A sine of B. Remember these are being multiplied together here. And then cosine of the difference of angles is going to be them the same thing, but with addition now. Cosine of A cosine of B plus sine of A sine of B. So as I promised, I'll show, look, if you're working with sine, it's like I think of it as the initial trig function that I want to think about, right? Like if I'm going to list them in some arbitrary order, all the trig functions, I'm going to start with sine, cosine, tangent. And that's just how it's in my mind. But again, you may have different experience, so you may approach it differently, and then it's going to end up in your mind in a different way. What I'm saying is, for me, if I think about it like that, then it's like, okay, sine. What I'm thinking about adding angles or subtracting angles. So with sine, if I'm adding the angles, then it's sine times cosine. And then when the angles are added with sine, the sine cosine multiplications are being added. So with sine adding, you're adding. And then with sine subtracting, you're subtracting. So maybe highlighter will be useful here. So with sine, when you add, and when you subtract, you subtract. And then with cosine, when you add, you subtract. And with cosine, when you subtract, you add. Now again, this isn't just going to jump out at you instantly and become second nature, but I'm just saying it's the more you write them down, the more of this will be familiar. And also, obviously here, right, you have with sine, you're multiplying sine times cosine in both instances. Because if you look at the right here, it's also sine times cosine, but it's in the reverse order. And this is written this way specifically so we can group these A, B, so we can do A, B, A, B. But I've absolutely also seen this right here written. I've definitely seen this written this way as well, right? So you'll see both of these in your time as an academic, right? Again, it's just sort of the way a certain person's mind works when they're writing this down. They're thinking, okay, I need to remember this trig identity. So when I'm working with sine and the angles are being added, it's sine, cosine, sine, cosine. I remember sine plus cosine, sine, cosine. But then it's A, B, B, A, right? You have to switch. But then another person, the way their mind works, they're going to think, well, when I'm adding sine, it's sine of A, cosine of B, and then cosine of A, sine of B. And then when sine is, when you have the difference of angles in a sine function, well, then you're looking at sine times sine A cosine B minus cosine A sine of B. Right. This is the kind of thing too that I'm adding these colors for you and your memorization. But if you make your own notes and you color it yourself, and again, you can choose which way you like. If you like AB angles, AB, or you like sine cosine, write it yourself and then label it or put colors on it yourself, and it'll sink in for sure. And as soon as your professor lectures about it, do your notes that day, that night. And that way it's fresh on your mind. Then you do the notes. As you're making the notes, it's going in your head. You also have the notes, and then when you go to bed, you're going to go into REM sleep, and that stuff's going to get locked into your, not just your RAM, but your hard drive, your long term. So we just know that the rule is when you're working with cosine, you're adding angles with cosine, then it's cos minus sine. And when you're working with cos and you have a difference of angles, then it's cos plus sine. All right. For somebody in a trig class, I mean, this is probably, if you haven't worked with it or seen it before, this is got to be the most challenging to just get down and stick to memory. But like I said, follow some of these strategies and I think it'll work out for you. Then we have, what I'm just going to write correlate, that if you have tangent of A plus B, well then I'm debating whether to even put this on your screen right now because it's a lot. I'm just going to write it. Just keep in mind that it's just a correlate of what I just showed you. So it's not the end of the world if you don't have this one memorized. If you're in a trig class that requires you to memorize the angle sum and angle difference of tangent, then you probably don't need me anyway because you're in a higher level class than I was. So this is equal to tangent A plus tangent B all over 1 minus what, tangent A times tangent B. That one seems honestly kind of simple to memorize too, right? It's tan A plus tan B over 1 minus tan A times tan B. Believe me or don't, this is actually a valuable tool, again, in a different class. I don't think you'll be quizzed to know this specifically, but if you happen to be, just know that all you would have to do is say, okay, if they say, what's this on the test? Well, then you're going to write this, right? Which you'll have to write out all this stuff. You'll write this over this. And once you do all that algebra and hopefully don't make any mistakes, it'll result in this. Which, if you do have to do that on a test in just an intro trig course, then may God have mercy on your soul. Okay, and last quick correlate of those is difference of angle within tangent, which is tangent of A minus tangent of B. And then you're not going to be surprised that it's now 1 plus tangent A tangent B, right? Isn't that interesting? It almost lines up. Like it looks like it should be like that, just visually. Okay, but we're going to get off of that one. Trig identities are fun, I'm telling you. So now that we're in the depths, we might as well go straight to double angle, which for sine says sine of 2 times x is always going to be equal to 2 times sine of x cosine of x. I'll be honest, I don't really want to write these parentheses, but I just feel like it's better for learning, but I never write them, and I'm only writing them now to be a good teacher. Okay? Again, this can be proved, or if you don't feel like trying to memorize this, I showed you on a problem in my last lecture that if you want to know sine of 2 times some theta, say we do sine of 2 theta, right? Well, that's, if this is theta, or I guess the way the problem works is you would start by finding, okay, say it's 60 degrees here, or pi over 3, right? Sine of 60 degrees, sine of pi over 3. You find the answer to that, and then you have sine of 2 theta now in your hands, but most likely, like the problem that we had in the previous lecture, is you're looking for theta. Say you found this in your work somehow. What is it? What's sine there? It's 1 root 3 over 2, right? Say you found that answer. Well, okay, if sine of 2 times my angle is root 3 over 2, sine of 60 degrees is root 3 over 2 over here, then you know that your theta is actually half of that theta. So the theta you're solving for is just 30 degrees. But now we're going to have a shortcut, which in my opinion, this is one of the easier identities to memorize. Right, it just says if you have sine of a double angle, sine of 2 times some angle, then you can break that into 2 times sine of x cosine of x. So you won't be surprised to find out what cosine of 2 times an angle is, what cosine of 2x is in this case, right? It's another correlate, right? So when you do sine of 2x, you're given 2 times sine of 1x times cosine of 1x, which we like that these have the same angle, and we mostly like it just being times a single. We don't like seeing this often. We want to, when we see this in an argument, we want to break it down and get just the angle out instead of twice the angle. And so cosine of 2x is, or another way to, and these are all conditional. This will be whatever you need it for in a problem. Or you have 1 minus 2 times sine squared of x, or you have 2 times cosine squared of x minus 1. And this may seem weird. Again, now you have 3 things that cosine of 2x is equal to, but you could also just think of it as you have more options, you have more things to work with. And again, I'll prove this real quick because it does seem like a lot. So I'm going to prove this one because it'll make me feel better about dropping all this on your shoulders, okay? The first thing I'll do, just as an exercise to show that I think it's true, right, is, so let's just pick an angle. We have cosine of 2 theta. Does it equal cosine squared of theta minus sine squared of theta, question mark? What if we just pick an angle like 30 degrees? Why not? Or pi over 6, we call it. So I'm just choosing this to be theta. So theta is pi over 6. All right. If I double pi over 6, okay, 2 theta then is going to be 2 pi over 6, or pi over 3, which is over here. If you still feel more comfortable with degrees, then just think of it like this. 30 degrees, 2 theta is 60 degrees. Okay. What is my coordinate here? It is 1/2. Why did I write it like that? It is 1/2, comma, root 3 over 2. All right. And then what is my coordinate right here? It's root 3 over 2, comma, 1/2. Yeah. Okay. So to answer this question mark, is this true? Well, cosine squared of theta is going to be cosine squared 30 degrees, or pi over 6, which is taking the x value here and squaring it. So it's going to be equal to root 3 over 2 squared, which equals 3 over 4. Okay. And then sine squared of 30 degrees, going to be the sine value here at 30 squared, which is 1 over 4. And then we'll say cosine squared of this theta 30 degrees minus sine squared of this theta 30 degrees will be this, putting them together, 3/4 minus 1/4 equals 2/4, which is 1/2. And then the question is that the same as cosine of 2 times theta? Well, cosine of 2 times theta, which is doubling 30 degrees, would be cosine of 60 degrees. And right here we have our 1/2. So that's I guess you could say the geometric way of proving it, the unit circle way of proving this first part, right? This is equal to this. Those are both equal to 1/2. All right. And then from that answer, I would like to show this 1 minus 2 sine squared x. Is that the same as cosine squared of x minus sine squared of x? 1 minus 2 times sine squared of x? Is that the case? Well, we can use the most basic of our identities to check if this is true, which was that cosine squared plus sine squared equals 1, right? here I have a 1, so I'm going to write this cos²x minus sin²x equals cos²x plus sin²x. Remember, this is 1. That's why I did that. And minus 2 sin²x. Okay, we still want to know, is this true? Well, I'm going to take this minus sin²x and add it to this side, which will result in a single sin²x over here. Or sorry, a single negative sin²x. And that'll leave us with this. Cos²x plus sin²x minus sin²x. Okay, is this true? Well, it's starting to come together, right? Subtract cos²x. Well, I see right here that we have sin²x minus sin²x equals 0. So then the next line is just cos²x equals cos²x. Is that true? Yes, it is, right? So, what was the third thing? The third one we want to know, does that also equal 2 times cos²x minus 1? We can use either one of these. We can use this left or this right. I'm just going to keep chaining it down the line. So we're going to say, is this true, right? If all 3 of these are true here, as I've claimed, if the yellow, the green, and the pink are all equal to one another, as well as equal to cosine of 2x, then this down here should be true. And let's see, to prove it, well, it shouldn't be too hard. We have a 1 over here. I'm going to subtract it from both sides. So I'll have this, and then I'll subtract this from both sides. This cosine²x from both sides. Sorry, 2 cosine²x from both sides. So that means we'll have minus 2 sin²x minus 2 cosine²x is equal to minus 2. Is this true? Well, since there's a minus 2 times this and a minus 2 times this, I can also say negative 2 times sin²x plus cosine²x, right? You can take this multiple of negative 2, multiple of negative 2, since it's happening to both. You just add them together in these parentheses and pull the minus 2 out. Well, is this true? And again, now we're back to our first identity, our favorite one, which is that this is 1. So that's just minus 2 times 1 is equal to minus 2. Yes, that's absolutely true. Yes. All right. So that was probably chaotic, but if you go back and slowly watch what I did step by step and try to make sense of it and practice it on your own, I promise those sorts of manipulations of all the trig functions come more naturally with time. And as a palate cleanser, this is called a co-function identity. These are free, right? Say you have, you're looking at 30 degrees, which we know is root 3 over 2 over to the x direction, and then 1/2 height. Okay. If you subtract your angle, which is just 30 degrees here, pi over 6, you subtract your angle from 90. So the co-angle, the co-function, this co-angle here, if this is pi over 6, and then this is 30 degrees, if you subtract the angle from 90, you end up with this 60, and that's going to be the same as cosine of your original angle, which you can see is true right here, because now our x is short and our y is long. So now these are our coordinates. Whenever you're working with that co-angle, you have co-function identity. It's true either direction you go. So sine of this is 90 degrees minus your angle is going to be cosine of that angle, and cosine of, if you subtract your angle from the 90, is going to be sine of that angle, right? It's just, this may have become obvious to you already, but it's just considered one of the identities, and I figured after that last mess, I might as well give you something easy to think about. Right, we did double angles, so if we do half angle, say we have some value. If you take half of your original angle, right, so you have 45 degrees, you take half of it, it's going to be plus or minus square root of 1 minus cosine of x over 2. Okay. Half angle identities, definitely look the most daunting. They look a little crazy, just glancing. Right, that looks a little wacky. You don't want to work with it. You don't want to memorize it. The best I can do for you is just to prove it, sort of. And it makes sense that to show that the half angle identities are true, we'll start with the double angle identities, so remember from double angle, we have cosine of 2 theta is equal to 1 minus cosine theta is equal to 1 minus 2 sine squared theta, right? You go back, I just showed that. I just declared that in the double angle identity. Okay, so we have, I'm going to use alpha. We're going to do a little bit of a let alpha be half of theta, right? So I want to cut theta in half just to give just to show something. So I'm just going to say let alpha equal half of theta. So then this is our double angle identity as I wrote on a previous page. Okay. It was written with theta before, but to show you something, I'm now going to use a different angle, alpha, which is half of your theta. So the rule still applies. No matter what this angle is, this will be true. So if this angle alpha happens to be half of theta, well, you could just picture in here, okay, I have half of theta in there. That's going to be, here's half of theta as well, okay? 2 times half of theta is just going to be theta. 1 minus 2 sine squared half of theta. If I solve this for sine, then I'm going to have cosine of theta minus this 1 equals negative 2 sine squared half of theta. Then if I divide both sides by negative 2, okay, if I do that, I get, we can just use this, sine squared theta over 2. All right, and a proper way to write this would actually be, if there's a minus sign in the denominator, that means the minus sign actually applies to this whole thing. So that's cosine of theta minus 1 over 2, all over 2, it should be said, right? And then I'm going to end up just putting the minus sign in the top for my own sake. So that would be, this is a positive cosine theta and a negative 1. So when I apply the minus sign to this numerator, then we're actually going to have a positive 1 and a negative cosine of theta. That still equals sine squared of the half angle, half theta. Then the last step is to take the square root of both sides of this. Remember, when you do that, if you take a square root, it's actually going to be plus or minus, because both the positive and the negative roots are solutions. And that's how we have this sine of the half angle is equal to plus or minus square root of 1 minus cosine x over 2. Again, looks a little crazy, but that's how we get it. So you derive the half angle formula from the double angle formula. All right, so we're going to do the same thing if you want to show it for sine. So we take the cosine double angle once again, which is equals 2 cosine squared alpha minus 1. And alpha is theta over 2. So cosine of 2 times theta over 2 is just theta equals 2 times cosine squared of theta over 2 minus 1. And we are interested in knowing what the half angle is equal to. So we start working by moving the -1 over here, and then I'll divide both sides by 2. Then I'll square root both sides, which, remember, when you do that, plus or minus. So that's how you get that part of it. So that shows that the cosine of half of an angle is equal to plus or minus the square root of cosine of the angle plus 1 divided by 2. And that's how you would do that. Okay? For tangent, it is this whole mess, which you may need for class one day if you go to that level, and you may not, but I'm not going to prove it right now. You can try proving it yourself if you want. Again, a hint is tangent is equal to sine over cosine. That's the hint. All right. And next we have a correlate of those half angle identities, which these actually are quite common, I believe. I've used these a lot of times in, like I said, mechanics, electricity and magnetism. And these come up. 1 squared x equals 1/2 of 1 plus cosine of 2x. Okay. And then tangent, we always throw in there. Again, all of the tangent identities are kind of a bonus. I don't expect that they would be on your test, but you never know. Maybe as a bonus question. These, once again, they look familiar. You know that sine squared plus cosine squared equals 1. And so you have to ask yourself, if you add a half of that thing to a half of that, would you expect to get 1, right? Do you think this equals 1? Would that be the craziest thing you've ever seen? It's not that crazy. And you can try that just as an exercise. I could sit here and prove every one of these things, every one of these identities and correlates, but I have a few problems that I hopefully will display some of the usefulness of this in those. So we also have some identities for trig functions, okay? And so if you're adding together a sine of an angle and a sine of a different angle, that is equivalent to, this sort of, to me, says the average of the angles if you add them together. Interesting. Sine of an angle minus sine of a different angle will be 2 times cosine of angle 1 and angle 2, or angle A and angle B. All right. And again, you'll notice there are interesting little patterns with the negative signs and the cosine and the sine. So, it's hard to just force it into your memory here, but you'll, as you practice, see, okay, if I'm adding if I'm adding the sine function of 2 different angles together, then I get 2 times sine times cosine, where the arguments of those are a plus b over 2, a minus b over 2. If I'm subtracting sine of angle b from sine of angle a, then I'm going to use 2 times cosine, a plus 2 times, and it's flipped, cosine of the angles added together divided by 2 times sine of the difference of the angles, the second angle being b, divided by 2. So then we have cosine of A plus cosine of B. So you're working with 2 different angles, and you're adding their cosines together. Well, then you get 2 times cosine of the angles added together divided by 2 times cosine of the angles B subtracted from A divided by 2. And if you have cosine of the first angle minus cosine of the second angle, well, you have this weird minus 2 sine of A plus B over 2 sine of A minus B over 2. Okay, so as you can see, what we've gone over is when I have 2 different angles, this one and this one, and this one, and I would like to add the signs of those, or subtract the signs, add the cosines, or subtract the cosines. Take the sine of the two angles added together, or take the sine of the difference of the angles. Take the cosine of the angles added together, or the difference of the angles. And the final identity, to me, not one that I'm super able to memorize, if I'm totally honest with you, is sine of this angle times cosine of that angle results in 1/2 of the sine of the added angles plus sine of the difference. And if you have cosine of first angle of this angle times sine of that angle, well, that's 1/2 of sine times a plus b minus sine of a minus b. And then if it comes down to cos, right? 1/2 of cosine a minus b plus cosine a plus b. And sine, we have 1/2 cosine a minus b minus cosine a plus b. Okay, that's the product identities. Enough torture. So remember, you need a reference sheet. You need to be working on your homework problems that are going to ask you just to get the problem that includes trig functions from one form to another, or it's going to specifically say use identities to show that this equality is true, or use this equality that we gave you to show an identity, a trig identity. You're going to have to just do problems with the reference sheet pulled up, and it's going to take, in my opinion, more than a semester to literally to know every one of these identities off the back of your hand. There's no reason to think I need to know every single one of these, especially including the tangent ones, for your upcoming exam in a trig class. There's just no way. It's just, and maybe I shouldn't have even written them all down. I just think it's good to write them down, and they use alpha and beta here instead of A and B, and then often they'll use X and Y, but I just did everything with capital A and capital B, so I just wanted to get them all in one location, all sort of cohesively put together. So that being said, that's all the trig identities that exist. We're going to practice with some of them right now, and you definitely don't need to know every single one of them by memory. There's just no way that that's even feasible. If your professor gives them to you and says, here, learn these, you're not going to come back the next week and be able to take a test on all of them. It just doesn't work like that. So let's go solve some problems and see how they're useful and when I decide that I need them, because I can predict that I'm going to look at the question and try to think, how am I going to solve this? And then this or that identity is going to become relevant at that time. Okay, so we have some problems. So number one, it's just asking tangent squared of theta minus secant squared of theta equals what? So why are identities useful? Well, there's one that tells us that tangent squared of theta plus 1 equals secant squared of theta, right? That's the first thing that jumps out at me. One of the identities we worked with appears to almost be in this problem from the get-go. Okay, so I'm starting off with this identity. It's one of the Pythagorean ones. So if I have tangent squared theta minus secant squared theta, maybe I could think, from this identity, I'm going to make tangent squared of theta minus secant squared of theta appear within it. So I'm going to do algebra on the identity and say tangent squared of theta minus secant squared of theta, right? You're allowed to do that. I got to keep this plus 1. And then I subtracted secant squared of theta from that side and from this side, so that equals 0. Then I can subtract this 1 from both sides, and that's it. Minus 1. Thanks to this identity, which if I did not have or I did not reference, would take a whole lot more work to show this. All right, number 2 says cosine of negative theta minus cosine of theta equals what? Okay, cosine is even, okay? So cosine of negative theta equals cosine of theta. So the problem we're given, cosine of negative theta minus cosine of theta, I'm going to say equals 0. Why? Because cosine of negative theta is the same as cosine of theta. Cosine of theta minus cosine of theta equals 0. Done. Easy one. That comes from our even-odd identities. The fact that cosine is even and sine is odd. Tangent is also odd. All right. This problem wants us to rewrite this in terms of cosine and sine. And I spoke about this. That's something that the reason this question has that in it is because that's something you tend to want to do to simplify things, make your life easier. In any trig equation, any problem you have related to trig, you will often you've probably seen me do it in many of these videos already. Every time I see tangent, I just write sine over cosine, and that it's automatic. It just comes out. So tangent of theta, they do the little dot there, but I'm just going to do this. That's going to be equal to sine of theta over cosine of theta, right? We're allowed to do that. And cosecant is which one? 1 over sine, right? It just says rewrite, but then you'd want to reduce this. So that's going to be sine multiplied by 1 there. A cosine's multiplied by sine on the bottom. Sine and sine cancel, so you have 1 over cosine. That could be your final answer, or that's also the same as secant of theta. These are both true. All right. Rewrite over a common denominator. We know how this works. Sine of theta plus cosine of theta over cosine of theta plus cosine of theta minus sine of theta over sine of theta over a common denominator is going to be, first thing I do is think, well, I'm going to multiply this whole thing by sine over sine because that's 1, and multiply this whole thing by cosine of cosine because that's 1, and you're allowed to multiply anything by 1. If I do that, then they're both going to be sine times cosine in the denominator. So I'm just going to put it real quick right here, sine theta over sine theta, and cosine theta over cosine theta. Just know that that's what I'm doing. That gives me sine theta in the numerator times sine theta plus cosine theta, and then the denominator now is sine theta cosine theta plus, and then this is being multiplied by cosine, so that's going to be cosine theta in the numerator, cosine theta minus sine theta over, and then cosine theta is also being multiplied in the denominator, so that's what we wanted. We now have the same denominator, which means we can just put this whole expression in one single numerator, but I'm going to rewrite it quickly. So sine's going to get distributed here, so it'll be sine squared theta plus sine theta cosine theta plus, and then this gets distributed, cosine squared theta minus sine theta cosine theta all over sine theta cosine theta. All right. There's some things that jump out at me here. We have a sine squared theta being added with this plus sign here to cosine theta, cosine squared theta. And every time I see that, I just turn into a 1. So that plus that is going to be a plus 1 up here. So I'll rewrite that. Sine theta cosine theta minus sine theta cosine theta plus 1 all over sine theta cosine theta, and sine theta cosine theta minus sine theta cosine theta. This is times, I should say. Sine times cosine minus sine times cosine is just 0. So we'll do that, 0, which equals 1 over sine cos is possibly your final answer. You could also write, since these are multiplied together, and they're both in the denominator, it's technically also a cosecant secant if you really want, you know. But depends how picky your professor is or what they expect, but both of those are true. Okay. This one says we would like you to multiply this fraction times this fraction. And obviously this already equals 1. You're not going to reduce it to 1 because what they're doing is they're giving you an exercise and showing you, right, how to use identities and how they appear sometimes. So that's why they want you to do this. Sin theta, when you multiply fractions by fractions, you just multiply the numerators and multiply the denominators. So sin theta times 1 is sin theta. Sin theta times negative cosine theta is going to be minus sin theta cosine theta, and that's going to be all over 1 plus cosine theta times 1 minus cosine theta. Okay, I imagine they want us to do something with this, so on the bottom here I'll distribute. That's going to be, so sin theta minus sin theta cos theta over a 1 minus cos theta plus cos theta, so you can see that's those two are going to cancel, and minus cos squared theta on the denominator here. So this is 0, meaning we have sin theta minus sin theta cosine theta all over 1 minus cosine squared theta. And at this point, I'm just trying to figure out why they want us to do this and what it's supposed to show. I mean, off the bat, this is not reduced, so I'm thinking, okay, so I'm going to turn this 1 into a sine squared plus cosine squared and see what happens. Right, so that's 0. So then we have sin theta minus sin theta cosine theta over sin squared theta. And then this, okay, we're kind of getting somewhere. It's a little weird. Now we have a denominator. What's happened now is we have a denominator that doesn't have any addition or subtraction happening, which is always nice, because now we can say, okay, this is sin theta over sin squared theta, and this is sin theta cosine theta over sin squared theta. And so now we have we got a little bit something new, so that's 1 over sine minus, now one of these sine thetas will cancel, and so this right here will result in cosine theta over sine theta, which I can say equals theta minus cotangent theta. It's hard to say if that's what they intended, if that's what they wanted you to do, but this is a very clean version of this up here, so yeah. I suppose the final answer could also be 1 minus cosine theta over sine. I don't see why not. Okay, this is definitely like a bonus problem. It took me a minute to really understand what the trick was on this one, but basically you have to just notice that this is a difference of squares, which is a bit out of our scope, and maybe I shouldn't have picked this problem, but it's a bit challenging, so we like it. This is the same as cosine theta plus 1 times cosine theta minus 1. To pick that out of thin air is hard to do, but you can do a check. Cosine squared theta plus a cosine, and then minus a cosine, and then minus 1. So there's your check. If you were to notice that, then we could rewrite this with that difference of squares in the numerator. Again, this may be out of the scope, but you will very well come across one of these problems and may just throw your hands up in the air and be like, what? You're going to try a few things and then end up with sort of just maybe going in loops and using identities that don't actually show anything new, and you're going to be like, what am I going to do? Try something out of the box, like say, oh, well, this right here is a difference of squares, perhaps that will save the day. And then cos² theta minus cos², I can also write this, right? This is the same as, you can pull cosine out, okay? So I'm going to pull the cosine out. Again, you might be thinking, why would I think to do this? Difference of squares. Well, you just sort of have to start throwing stuff at it, throwing techniques at the problem, because when this pops out, it's just like, boom, solved. So thankful. You know, you're just like, let's go. That's equal to 1. Therefore, I can just cancel them and say cosine theta plus 1 over cosine theta, which is the same as cos over cos plus 1 over cos, which is the same as 1 plus secant. So I'd say this is the simplest form. But yeah, that one's using more techniques than just identities. It helps to have a little bit of a more challenging problem to look at. Because if you practice on challenging problems, then anything easier than that that's on your test, you should just automatically destroy. Okay, so by establishing each identity, it's saying basically use identities to transform this into an identity, I believe. So cosecant is 1 over sine. Cosine we can just keep. And cotangent over here is cosine over sine. And so cosine over sine equals cosine over sine. That is true. They just want you to be able to manipulate cosecant and cotangent to say, is this true? Kind of a thing. Okay. And then here we have tangent, which is odd. Instantly jumps out at me. Tangent odd. So tangent of a negative argument is going to be equal to the negative tangent of the positive version of that argument. Okay, so this is a little bit tricky, but if you just pay attention, things can line up for you. Tangent of negative theta is equal to negative tangent theta, but tangent squared of negative theta is not equal to negative tangent squared of theta. You cannot do this. So what we can do is say, okay, tangent squared of negative theta, that's the same as tangent negative theta times tangent negative theta, right? This we're allowed to do, yes, and that equals secant squared theta still. And then each of these I'm allowed to say is 1 plus, here we go, I'm allowed to say is negative tangent of theta times negative tangent of theta. So these two negative thetas being multiplied by one another result in a tangent squared theta, positive. So 1 plus tangent squared theta equals secant squared theta, and that is our identity that we're looking for. Good. What was the identity we're looking for here, though, is the question. Just to go back, so I think that what they wanted is, once I put the cosine over the sine, then, you know, this is cotangent theta. I guess this is the identity they were interested in. Yeah. So a lot of times in your trig class, they will have you, you know, keep this side cotangent the whole time and then do all your work on this side. So then at the end, your solution would say cosine theta over sine theta is equal to cotangent theta, because this is technically your identity, but that works. Okay, and last thing, let's see, we have, I'm just going to turn these into what I know that they are in sine and cosine. This is a perfect example of how to use that knowledge. So sine over cos, cos over sine, and 1 over sine. Okay, this is here, this is here, this is here. And we keep going. We say multiply these across, so sine theta cosine theta over cosine plus cosine squared over sine equals 1 over sine. Okay, interesting. Then we might say, how can we make these sort of work better together? So if I multiply this side by sine theta, we're just going to be left with 1. If I multiply this whole thing by sine theta over here, we're going to get sine squared theta cosine theta over cosine plus, you just distribute the sine, plus sine theta cosine squared theta over sine. It's getting interesting. And remember, that's equal to 1. So what is this reduced to? Look at that. Cancel the cosines, cancel these sines, and that's the Pythagorean identity. Cosine squared plus sine squared equals 1. Beautiful how that works out. Hope that one helps. I'll see you in the next video.